Okay, so welcome back, and now before we get into the proof, I do want to just mention or just notice, I don't know if I said this in the last video, but notice that these two vectors are the beta vectors that we are talked about in the lemma. So here is beta 1 and beta 2. So you notice how we're able to rewrite everything as a linear combination of the free variables in this case. So now part of the proof of induction, there's two parts of it. One is the base step, and then we have the induction step. So let's start with the base step, and we'll show that this is true for that all, right? That's what we're trying to prove, that all vectors can be written as a linear combination of the free variables, okay? Okay, so let's start with the bottommost equation, okay? So we're assuming, right? Well, first of all, we're assuming that this is trivially true if there's for all zeros, right? If we have 0 equals 0, then we know that this is going to be trivially true. So we're going to assume there are no 0 equals zeros. We're going to ignore those because for that reason, okay? And also because this is a homogeneous system, then there are no contradictory equations, okay? So we're going to use induction to verify that each of the leading variables can be expressed in terms of the free variables, and so that we're going to finish the proof. That will finish the proof because we can then use the free variables as parameters, and then the beta variables, right? The beta vectors are going to be the vectors of the coefficients of those free variables that we saw in the last video, okay? So we're going to consider the bottommost equation, okay? So let's assume that we have the bottommost equation, and we're assuming it's an echelon form, right? So this is what we're going to have, okay? So let this be our bottommost equation. Okay, now, in this case here, this L sub m represents the leading variable. Okay? So x sub L sub m is the leading variable in the mth row. Okay, so this is going to be the last row, right? That's what we're assuming. We're at the bottommost row. Okay? Now, the thing is any variables that are going to be to the right of this variable are then automatically free variables, right? They have to be free by what we're starting with, okay? So we're going to move these to the right. So let's finish this off before we do that. So we have plus what do I want to use for that? Yeah, we'll do m plus 1. Oops, hold on a second. Plus 1, like that, times x sub L sub m plus 1, okay? Because it's the next variable, right? So here's the first free variable, and then we'll continue in like fashion until we get to the final variable, which is going to be a sub m comma n times x sub n. Right? So remember, dealing with matrices, so m comma n, right? And then of course this equals 0. And now since all of these are free variables, we're going to move them to the right. And then, oh, by the way, we're also assuming that this leading coefficient here is non-zero for obvious reasons, right? We can't divide by 0 because we're going to solve for the bottommost leading variable, okay? We can't divide by 0. It makes no sense that the leading coefficient would be 0, okay? So we're going to assume that it's non-zero. And so if we solve for x sub L sub m, this is what we get. Okay? And in this case, we're going to get negative, right? Start with negative m, a sub m comma L sub m plus 1. And then times the first free variable, which is x sub L sub m plus 1. All right? And then we're going to divide that by this. A sub m comma L sub m. Right? And so we can then simplify this a little bit more, and let's pull this variable out so we can see that what the new variable is going to look like. So this will actually be this number divided by this number, so it'll be a sub m comma L sub m times x sub L sub m plus 1. And then plus, well, what do we get? We're going to do this for all of these, and so plus dot 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 plus, and then we're going to get what? We're going to get minus a sub m comma n divided by, again, a sub m comma L sub m plus 1 times x, sorry, my handwriting's a little too big, x sub n okay, and so we do this to express the leading variable in terms of the free variables, right? Now, it says here, there is a tricky technical point here. It says if the bottom equation here, right, this equation here is what? Okay, so there are no variables to the right of the leading variable. Then that would mean that x sub L sub 1 or x sub L sub m is equal to 0, right? Which is trivially true. And satisfies the statement that we're trying to verify because, as we alluded to before, it's written as a sum of the number of free variables. And so under the convention that, namely the sum of 0, in that case, it would be 0 free variables. Okay, so it would be trivially true. Okay. So let's say, so this is the thing. So we can show that the bottom step, right? We can show that any bottommost equation, right, can be written this way with those assumptions, right? And so now that's the base part. Now let's do the induction part. Okay, so now we're going to assume that the statement holds for the bottommost, let's say, t rows. Okay? So we showed it for the bottom row, right? Let's assume that it also holds for the bottommost t rows. T being some number, right? It could be, let's say we assume that this holds for the two most bottom rows, or the three most bottom rows, or the 4 or 5. Just some t number of rows, bottommost rows that we're going to start with. We're going to assume that, right? Now all we have to do is show that it also applies to the t plus the t plus 1 bottommost row, right? Or is it t minus 1? Yeah. So let's just assume that it holds for the bottom t rows. And then we'll show that it holds for the I think it's t minus 1 rows. Okay? So let's start with that. So we showed it for this particular bottom row. Now we're going to say let's assume that it holds for the bottommost t rows. It's hard to understand that, right? So t is just some number of rows that we're going to assume that it holds for. Okay? And so t, right? So t is going to be some number that's going to be greater than or equal to 0. Right? Because that would be the bottom row. If it was t was equal to 0, it would be the bottommost row. So it's going to be where t is an element of this range, right? 0, well, let's just put colons. So t such that t is greater than or equal to 0 or less than n minus 1. Okay? So what we're going to do is we're going to assume that for the mth equation and the m minus 1th equation, and etc., 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 up to and including the m minus tth equation, we can go ahead and express the leading variable in terms of the free ones. That's what we're assuming. Okay, now what we're going to do is we're going to verify that it will hold for the next equation up above above those equations. Okay, which is going to be this equation, right? We want to show that it satisfies for the m minus t plus 1, right? So it's going to be the next equation up. Right, so it'd be for right, so we're going to assume that it holds for all of the bottom equations, from the very bottom equation all the way up to the n minus 1th equation. So these are the bottom equations we're going to assume that it holds for. Okay. Then now all we have to do is show that it holds for the next equation above in the matrix, right? In the system of equations, because we're working for the bottom up, like we've been doing. Okay, now, in order to do that, we're going to take each variable that leads in a lower equation, right? So that's going to be all of these variables. Okay, so again, we're going to take all of these variables. So x sub x sub L sub m all the way to x sub L sub m minus t. Right. So these are all the leading variables. And we're going to substitute its expression in terms of the free variables. Now, we only need expressions for the leading variables from lower equations because the system is in echelon form, remember. So the leading variables in equations above this one do not appear in this equation. Right? So then the result has a leading term of what? The leading term is going to be what? It's going to be a sub m minus t plus 1, comma, L sub m minus t plus 1. And again, not equal to 0. And the rest of the left-hand side is a linear combination of free variables. We know that. So then if we move the free variables to the right side and then divide by this leading coefficient, then what did we just do? We end with this equation's leading variable, which is going to be the x sub L sub m minus the quantity t plus 1 in terms of the free variables, which is what we set out to do. And so that's the idea behind the inductive step, right? So what we've done is we did it for a base step, right, which was we showed that it works for the bottommost equation. Then we assumed that this also applies to all of the equations for the bottommost t rows, right? And then we showed that by induction it holds for the next row up, and by doing so, by induction we've showed that it has to be true for all of the rows going all the way up to the top row, because the pattern we just proved that it goes on, the pattern continues on until the end, which is at the top. Okay, and so therefore proving what we set out to prove, which is that we can set all of the we can write all of the leading variables in terms of the free ones. In other words, then it makes sense that at the end we're going to end up with these vectors, the beta vectors, and we're going to have a linear combination of these beta vectors and the free variables. Okay. And then of course what we've done is that we can parameterize solution sets using free variables, right? So, which is sort of what we've been doing. We've been using the echelon form, and then we parameterize the each one of the equations in terms of the free variables, and then we've been writing it in these vector form, right? So we have all these beta vectors, and then of course it's a linear combination of these beta vectors along with the free variables. And we showed that this will work for all. We could do this for all of the leading variables, okay? Now, we say that the set of vectors, right? So again, we've got these set of vectors, right? Just like in the lemma. Okay, so we have these set of vectors. Right? I don't want to write plus. Okay, so here's, excuse me. Okay, we say that the set of vectors, okay, oh, hold on, these are pluses. Is generated by or spanned by the set of vectors beta 1 through beta k. Okay, so we would say that all the set of vectors, right, that are represented by this linear combination of these vectors with these coefficients, right, that are all real numbers, is generated by, so the terminology were generated by, or spanned by these set of vectors. Okay, so that's going to be very important because we're going to use this terminology quite a bit, right? We're going to talk about spanning sets and whatnot. Okay, so now to finish the proof of theorem 1 that we introduced before, right? A few videos before, we're going to now introduce a second lemma. Remember, we're going to use two lemmas to prove the theorem. Okay, so we just did the first lemma, went through the proof. Now we're going to talk about the second lemma in the next video. Have a great day.